Hi there. So as I mentioned in the last video, I wanted to go over an extension of the volume problem that rather than copies an audio file exactly as it is with a different volume, we're going to be creating entirely new sounds out of an input file using a technique known as granular synthesis. Synthesis here is like a little bit of a misnomer because we're not really generating any sound. We're taking existing material and just scrambling it up to the point that it is almost unrecognizable depending on the certain parameters that you give it. So let's get into it. Most of the setup for this is going to be exactly the same. What's different is we have a slightly different check for the command line arguments just to see if everything's running properly. Before we were checking just for having 4 arguments. Now we want anywhere from 4 to 6 because if we do want to just run the volume program, we can, and that would take 4 arguments. If we do want to run this, what I'm calling scramble, we would need 6. There's definitely a better way to do this to check more specifically, but no one else is ever going to be using this program, so I've just left it as is. Not too worried about it. The other thing that is different about our setup is going to be this srand. So we're seeding our random. And we're going to be using some randomization later, and all this does is it gets our current Unix time to seed the randomization. That way we get a different random number every time we run this program. If we didn't do that, we would be getting the same numbers in the same order every time we ran this. So in order to do that, we need to include the time library, and that's really all we're using it for. Next, we will need to include the string library as well so we can use stir compare. And that's just to check our command line arguments to see if this scramble has been called at this position. But a lot of this, like I said, is going to be exactly the same. So we do need to copy our wave header from our input to our output. And we're doing this exactly in the same way as from volume. So I'm not going to bother explaining it. If any of this does look unfamiliar, and you want a more thorough understanding of it, you can check out my previous video on volume or any other explanation on the CS50 Lab 4, and you'll be able to get a better understanding of how this is all working from like a setup phase and how kind of fread and fwrite are working here and why we're getting all these values and all that stuff. But for now, we're just going to talk about this granular synthesis aspect. So the first step, let's say we have actually called this. We're actually going to run this aspect of the code. And the first thing we need to do is get our input size, which is going to be the size in bytes of our input file. So we're going to call this function getFileSize using the argument with the file path of our input file. So let's go down to getFileSize. And let's see what's happening here. So we called it with the argument of our input file. So that's what we have here. We're opening it, same way we've used fopen before. The only difference is now we're doing RB mode. We're reading in binary mode. And the reason we're doing that is if you just use R, you're reading it in text mode. And there are some things that are going to be changed. Like it's going to look for things like empty space and like line characters like \n, things like that, and it's going to actually interpret that. And we don't really want that in this case. I'm not convinced this actually makes a difference, but because we don't want to make use of any of that feature, there's really no reason not to use RB rather than R. So that's why just this one character is different. Some error handling just in case it can't open that file. And then here's how we actually get the size of that file. So we're going to be using fseek. And the way that works is it takes the file. In this case, this is our input.wave that we've sent in through here. It gives you an offset, and then you have like these special values here. So seek end, like it says here, it's going to EOF, which is end of file. So it goes to the very last byte of your file with an offset of 0, because we want to be at the very end, so we're not offsetting it at all. So this is saying that internal counter that this file structure is holding onto for us, that when we use fread and fwrite, it knows where we are. We're moving that counter to the very, very end. And then we're declaring a long integer called size. And what we're putting into size is the return value of ftell. So we've moved with fseek to the very end. ftell is just going to return where we are. So we've moved to the very end. ftell is going to return the number of the very last byte of this file. And with that, we've essentially gotten the length of this file in bytes. And then we've just got to close the file and return size. So now we're back up here. There could potentially be a better way to do this where, I've opened that file again down there and then closed it just so I could have it open and closed again here. So there might be a better way to do that. But like I said, I just kind of threw this together. I'm not really worried about optimization given that nobody else is ever going to use this. So that's how we're getting our input file size. And what we're doing with that is just allocating a big chunk of memory that is exactly that same size. We're calling it buffer, and it's going to store 16-bit integers. All right, so buffer is going to be the name we use as a pointer to that allocated memory. So that's what malloc is going to return to us. It's going to return a pointer. All right, so let's keep going. So something else we're going to need is the number of audio samples in that file. So we're doing two things here. We're going to actually do this reading from the input to the buffer. So we're essentially copying the entirety of that input in 2-byte chunks to the buffer. And let me kind of go through this a little bit more detail. We're reading from our input, which is in this case our input.wave, the amount of items that we want to read are input size, which is the amount of bytes in this file, divided by 2. That's because each audio sample is going to be 2 bytes, which is something we went over in the last video. It's the bit depth, which in this case is 16, times the number of channels, which in this case is 2. So this actually, I'm going to go over. This is a little bit misleading. So the bytes per sample is just a known formula. It's bit depth times number of channels divided by 8. This is going to give us the amount of bytes per each sample, including every channel that exists. So if we're working with a 2-channel file with a bit depth of 16, it's going to be 4 bytes per sample. But that's saying that there's 2 bytes in your left and there's 2 bytes in your right. And that's what we're really working with. We're working with each sample individually. We don't want that whole chunk. We want a left sample to do something with and then a right sample to do something with. So that's why this formula is actually a little bit misleading, because we want to work with 1 channel at a time. Even though our audio file has 2 channels, the number of channels that we're working with here is 1. So it's still 16 divided by 8, giving us 2 bytes per sample. Okay, so we're reading every sample into our buffer. So we're just copying the entire input file into our buffer that we've just allocated all this memory for. All right, and we're using the data type size t, which is an unsigned integer specifically for storing like the length of things. And it's good for things like this specifically because it's going to work with your computer's architecture to give you just pretty much the largest amount that it can hold. That way you're always able to store whatever number you need to store in there. It's not good for every scenario because, on a 32-bit machine versus a 64-bit machine, you're going to get a different amount of memory here. And if you want to be really specific with it, that's maybe not going to be helpful. But for something like this is exactly what it's designed for. It wants to store like the length of things. So that's why we're using a size T here. All right, so now we have an integer called chunk size. And this is something the user is going to specify. And this is like the amount of samples that we want to rearrange at once. If our chunk size is 1, we're going to take every individual sample and randomly place it somewhere else. If our chunk size is 1,000, we're going to take a chunk of 1,000 samples and put it here, and then another 1,000 and put it here. So this is just going to change the sound pretty drastically, and it's just a parameter that the user can mess around with. And then range is another user input parameter, which is going to be a range that your chunk size can be in. So meaning like if you'd say a chunk size of 10,000 samples with a range of 5,000, your chunk size will be randomly chosen anywhere from 7,500 to 12,500. And this is just useful if you don't want any rhythmic pattern. If you do 10,000 with 0 range, every chunk is going to be 10,000 samples long, and you will hear a rhythm with that. You'll hear a constant pace. If you don't want a constant pace, you can set this range to be a very large value, and then you're going to get a randomly sized chunk, and there will be no discernible pattern coming out of that. So this could be 0. This is only like a user preference kind of thing, range. Okay, and then now we're actually doing the granulation. I don't know what the word is. So the pattern here is going to be that we're taking this buffer that currently has the entire input file, and we are randomly choosing a place in that buffer. We grab a chunk from our user specified chunk size, starting at that randomly chosen place in the buffer, and then writing that to the beginning of our output. And then we're just going to keep going over the amount of times specified here. So the output is actually being written top to bottom, grabbing from random spots in our temporary buffer, which currently represents just our input file. So how are we doing that exactly? We have a for loop that's going to run this code this amount of times. So our total number of samples divided by our chunk size. If you have 50,000 samples and your chunk size is 25,000, you're only going to have 2 chunks. So you want to run this thing twice. Ideally, we're going to be using much smaller chunk sizes and much larger files with many more samples in them. So you'll have more than 2 chunks to be rearranged. You'll have many, many thousands of chunks to be moved around and to create some new sound out of that. All right, so for every time, we're going to pick a random index, and that's just running the random that we seeded earlier, modulo by the number of samples. So this is just going to pick a random spot in that temporary buffer to take information from. All right, so that's how we know where we're going to read from. And then let's look at the rest of this fwrite function. So we're going from our buffer at a random point within that buffer to our output. All right, how many samples are we going to read? We're going to read this many samples. So let's imagine that this is 0 for a second, that our range is 0. So it's going to be 0 plus our chunk size. So let's say our chunk size is 1,000. We're going to read 1,000 items that are the size of 1 audio sample, or 2 bytes here. Okay, if our range is larger, we're just doing a little bit of math here to pick randomly anywhere from our chunk size minus half of the range to plus half of the range. So if your random goes right in the middle, it'll be exactly your chunk size. If it goes to its lowest possible, it's going to be below. Higher, you get how basic math works. So that's pretty much how this works. That's how we get the amount of iterations we want to do. This is how we determine where we're going to grab from randomly. And this is how we actually do the writing. And that is pretty much how this goes. So in order to test this, I just had this like lo-fi hip hop kind of sound. Regular music. And then we're going to run it with a chunk size of, you know what, let's make it really big. Let's do 10,000. So we're going to take 10,000 sample chunks and rearrange them. And here's what we get. So we have that sort of rhythm, right? Because our range is just 1, so basically nothing. So we have digga, 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 digga. Let's see if we make that, 9,999. See if we can get rid of that rhythm. Okay, so it's almost rhythmic because the input source is very rhythmic. But let's say we make this a much wider possible range and see what happens there. So it's much more stuttery. It seems to be much more random. But the point of this is to generate new sounds. So these are very recognizable to the input source. So let's bring it down to like 2,000 and see what that sounds like. Now we're getting something kind of funky. And what I really like about this is that as we approach 1, we get closer and closer to pure white noise. Where when we do 1, and because this is random, theoretically it could be the exact same file that gets outputted, but that will never happen in reality. So if we do this, we get pure noise. I think my favorites are right around here where it's real grumbly and bubbly. And this might not be like a great sound on its own, but I feel like if you were to filter this in a certain way or maybe run it through some other effects, you get some really interesting, really unique things. So that is granular synthesis and how to implement it in C. Hopefully that was a little helpful for you. If you look closely, you can see there is a lot of opportunity for this to be improved. Like I said, the error handling is not very thorough here. And then if you noticed, I'm kind of just working with the whole file size where the first 44 bytes are part of the header, and you may not want that as part of your granulation. Another thing is that, this random index could choose, 5 samples from the end, but if you have a chunk size of 10,000 samples, there's obviously an issue there. And that's what causes a lot of the artifacts and like weird extraneous sounds that might come in here. But for the purpose of this experimentation, I really didn't mind that, and I kind of like the output that it comes with. So yeah, not perfect, but for a general explanation of the concept, it does its job. So thank you for watching, and I will see you later.